Okay, so this is quxlang's devlog 2. Um, I'm gonna go through kind of just the progress of the language and what's here. So we do have actually multiple module support working here. So we use this file called quxbuild.yaml. We have our targets. In this case, I'm using the ARM64 target for all the examples. And you basically say, here's your module name. So each module, foo, bar, for example, and then you give it a source. So you can have, more than one um, version of a library in your modules directory. And you could say, for example, here's barlib 2.0 and here's barlib 2.1. And then you can say, okay, here's the source for this version, and then you can use a different version on a different platform if you need to. So for example, if there's some compatibility issues, you can have different um, modules be checked out at different revisions. So you could do that. So that's where you have this modules folder, and then you have this sort of relative source, and you say, okay, what is the source? And so the idea here would kind of be that I would have, I don't know, if I want to use the runtime module, it could be in this module or whatever. And it will load this from the folder, which is going to have, we have this module.yml file, which is not being used currently, and then you have the sources folder. But any kind of module specific stuff is probably going to go in that module folder or YML file. I may rename it, but so this is the main one that I've got here. So you can see that this actually contains two functions or two files, sorry. And so we have this other file function here, and this is able to pull the other file. So we have this test, and then that's actually checking a function from another file. And then I believe we also use foolib somewhere. So we're able to call foolib imported function, and that's in here. So we can check that this actually works. So multiple modules do work at this time. And so you can have different modules, you download them, put them in the same directory. However, you get that into position, and then you just kind of run this on it. So multiple modules do work. We do have string constants now as well. But let's go through something. So serialize doesn't currently work. That's kind of one of the next steps. But so we have arrays, for example, and now we have default constructors working for non-trivial types. So before we only had arrays of trivial types, and now it works for any type. So for example, this type has a constructor, and this constructor is able to execute as well, and it's going to able to execute for each of the things in the array, which was a little bit of a painful thing to do because of the way that this interacts with like unwinding, but not too bad. Um, so array literals are still to do. We have runtime statements now. So for example, I could say if I'm in const_expr, I do runtime const_expr, else I do this other thing, and you can do that. Now there's this kind of string class, which is not really fully implemented yet, but we can take a string constant as a parameter, and this object has a .begin and .end property, and so you can think of it as an array where it's got this begin iterator and an end iterator, and it's going to be pointers to bytes. So these are bytes, and you can do whatever you want with this begin and end, or you can create a loop and loop over them. Yeah, so that's the idea. We do still need to add this memory allocation to const_expr before we can actually create a string class, and then of course native allocation will also need to be added. And then we have this sort of playsat statement. This is also needs to be implemented. It does parse, but we don't actually have placement constructors yet. But the syntax parsing is working, and so this parses into the abstract syntax tree, and it doesn't do anything yet, but we can at least parse it. Okay, so we've also got this option statement. This is another parsing but not implemented yet thing. But anyway, so we've got constructors, we have destructors. So we have our arrays like this. So it's like var name of variable and then the type, and then arrays are these brackets followed by the type. And then you have the string, or sorry, it's not string, this size. And we have our if statements. This is our, array pointers. So we have a different type for array pointers versus instance pointer. This is getting the address. So this is kind of like, in C++, this would be like the same as that, where it's like, and y is the address of y. This is like, get me a pointer to y. So I have this thing, and then I want a pointer to it, and that's this arrow. Whereas if I have a pointer, let's say, z is a pointer, and I want the value pointed by it, I do it like this, because that's like the opposite, I guess. I don't know. Anyway, that's the syntax for pointers, for instance pointers. And then array pointers work a bit more like C++, where you could just go, q, or, if I have q address of 0, this is getting the 0 element, or 0id element. And I can then say like this 0, or maybe I could do like the value pointed by it, kind of like a regular instance pointer. So array pointers and instance pointers are similar, but you just have this extra like instance pointer thing that's like a pointer you can't do array arithmetic on. You can't add or subtract from instance pointers, and that's just designed to make it a little bit more optimizable and a little bit less error prone. If you have a pointer to one thing, you can just ensure that it's either null or it's not null. You can't do any arithmetic on it. Okay, and then we have like template expressions or templatic expressions, where we have this sort of templating type or templating parameter, and that's like auto is a templating parameter. So if I pass in something, it takes the type and sticks it in T1, and then we can call this. So for example, if we do this yip function here, it can take this i32 and it returns an i32 because it glues this, this type of this a variable is auto, and then it sticks the type in T1, and then that's also the return type. So we're able to sort of figure out what the return type is that way. Yeah. So we can create, expressions and stuff. And we can also, we have like enable if. So in this test, for example, the include if overloads, you can see it's like 0 as i16 is equal to 1, because it's going to say, okay, these are all i16, but this is going to run this enable if, right? And then it's going to evaluate this expression, and that's going to be true or false. And based on whether it's true or false, the overload is enabled or not enabled. So we can, make some overload work or not work. So we can run this test. You can see it passes all the tests, right? So if I just to show you that this does work, I'm just going to say this equals 9, and then I'm going to run this again. And you can see that it fails. It's going to fail at this assert instruction, and I need to fix this part. But you can see that we have an assertion failed where x equals 9 did not pass, right? So it creates this assert instruction. But of course, that should be equal to 1. So we can see that this is actually working, at least in the const expert. And we have, so, bits expression. Destructors. This is kind of some syntax I was thinking about for lambda expressions. This doesn't work, so I don't know. Will this be an error? No, I don't think I call this anywhere. Yeah, okay. And then here's the swap operation. This is like less than dash greater than. So that's the swap. It's an operator. So you just say x and other dot x, and that's the swap. Temporary references are not double ampersand like they are in C++. They are just this temp amp thing. So like you can write like const amp or const amp like this, or you can write temp amp, or you can do mute amp, or there's also write amp. So if you have a write only variable, so like for example, I don't know, there are reasons you might want to have that. So you can have write and then you can also have this mute and, which is also just the same as just a single ampersand. So if you just do ampersand, it works the same way as in C++, where it's kind of like that's just a reference, but you can also just stick the word mute in front if you want. We have this double question mark, which is called booleate, and this is like testing if a value is equal to 0 or not. So this is, or null pointer. So like this is like, is it equal to null pointer? If it's not equal to null pointer, right? This is like, is this non-null? And then do this if so. Because if you put a pointer in an if statement, a pointer is not implicitly convertible to a Boolean. So you cannot like do if x, where x is an integer or a pointer. You have to convert it to a Boolean with this test, right? And there's this sort of built-in booleate operator that'll convert integers or pointers into a bool. So this, like, if I want to know, is this a null pointer or whatever, I use this. And this is also intended to be used for like error types or anything else where you might want to have an implicit Boolean, but it's not logically a Boolean, because I want to make sure that like this expression is actually a Boolean, and there's no like I don't want to make it implicitly convert, basically, for most things. I think that C++ has too many implicit conversions in places it shouldn't happen. So this is one of those changes that we've made to make this a little bit more explicit. You'll also notice, for example, if I have a member variable, I have to use dot. You cannot refer to this like this. It will not compile. You have to put a dot in front, and that's like this dot, kind of like this. It's the same thing, but it's just a dot like this, right? It's like dot y, and that's the same as putting this dot y. Those are equivalent. So we can take string constants. These are byte, constant pointer to bytes. And then these are the string constants. And this is a not accurate Roman numeral parsing, but I just, of course, this is very simplified. Well, it's less than end if it's equal to I, value plus equals 1, and dot value equals value plus 5 if it's equal to 5. And this is like, this was earlier. We actually didn't have character constants for a little while, so I had to do this. This is not necessary anymore, but you can see like this is a string constant. We can then take its beginning and then get the first element from it. And then we just increase the iterator by 1. And so these are pointers, we can increment them. Same way as in C++. We have iterators. And then we have swap. So you can say a equals 5, y equals 10, do this, and then a equals 10 and y equals 5. So this is like an exchange or swap operator, and that's built in for all the primitive types. Import things. We have string constants. We have this as for conversion. So you'd be like x as something to do the like implicit conversion instead of directly calling the constructor, or calling like a static cast function. That's just kind of a syntax. We have named arguments. So for example, we have this test argument passing helper, which is somewhere. But you can see that in this case, I pass them in this order, and in this case down here, I pass them in this order. Actually, this is not running because static tests don't work yet, but in principle, it doesn't matter which order they get passed in. So if I find this somewhere else in the code, you can see that this actually takes the arg first and then the integer. But this actually will compile just fine over here with taking the integer first and then the argument, because these are named arguments. So it's actually based on the named parameters rather than the position that they're in. So I can call functions like this, and the idea is that this syntax will make it much harder to make a lot of mistakes where you like, I don't know, put source and destination backwards, because I found that to be a very common cause of mistakes when people are programming, especially with like, algorithms and stuff where they take like 8 iterators. Okay. And so let's go back. And we have bitwise operators. Bitwise operators some of them are a little different. So instead of doing shift left and right, we have up and down. So for example, hash plus plus is a shift up, which is essentially equivalent to shift left in other languages. So for example, if I shift up by 1, that increases each sort of component power of 2 by 1. So this has, the 2 to the, what is it, 2 to the second, or no, well, 2 to the first and 2 to the 0th, right? So this becomes 2 to the second and 2 to the first, right? So each component power of 2 is increased by 1, and that's how you think about this. So this is kind of the same thing, but shifting down. So each component power of 2 is decreased by 1. So this is the component power of 2 squared, or 2 to the second power, right? So since this is 2 to the second, this becomes 2 to the first, right? So that's a equals 2. So this is 2 to the first plus 2 to the second, right? And therefore, because that's equal to, right? And this is math here. That's equal to 2 to the second plus 2 to the first, like that, which when we add 1 becomes 2 to the 2 raised to the, hang on, sorry, 2 to the first plus 2 to the 0, sorry. Okay, my bad. But you can see this is 2 to the first plus 2 to the second. I was like, did I do some math wrong? Yes, I did. But you can see like this is 2 to the 0 plus 2 to 1. So when we increase this by 1, all of these numbers go up by 1, right? So another way to look at this would be like, let's say I'm looking at 101, which should be, that would be like, what? This is 1, 4 plus 1, so that'd be 5. So if I say this is 5, right, and I increase this by 1, that would be like 2 to the 0 plus 2 to the second, right? And then that would become 2 to the first plus 2 to the third, which is, so this is going to be 8 plus 1 is 9. So if I increase this by 1, that's going to be equal to 9, right? No? Am I doing math wrong? Hang on. So this is 2 to the second. Oh, sorry, 10. Yes, okay, so this is equal to 10, right? And so that's 2 to the first plus 2 to the third. You can see we've increased each of the powers by 1. And you could do the same thing with like plus 2 or whatever. So for example, a equals a plus 2. So this is equal to 2. So we increase it by 2. So that is, this is equal to 2 raised to the first power. And then it becomes 2 raised to the third power. And so this is a little bit of a difference between thinking about this in terms of shifting. And the reason why I wanted to look at it this way is mainly because this becomes very confusing for people that are from a mathematical background with the left and right shift. I think it's a little more confusing. And also, if we shift up, we're making the number bigger, same as round up. If we shift down, we're making the number smaller, same as round down. And then also it allows us to work with big endian representations of integers and still have them work, which is very convenient because a lot of the math in computers is in little endian. And if I want to represent arrays in left to right order, this it makes it very inconvenient to use big endian binary representations, because then it's like a zigzag ordering of bits, and it's just annoying to work with and represent, especially for like compression algorithms and stuff. But we have additional operators. So every like if we have this logical and, we just put a hash in front of it, and that's bitwise and. This is or, and so adding a hash in front, that's bitwise or bitwise or. This is OR, bitwise exclusive OR. We have up rotate and down rotate here. So just change out the last one for a percentage sign, and that's a rotate operation. So we have NAND, we have NOR, and NXOR if you want to use that. And then I need to implement this, but this is bitwise complement. And we also have rotate operations again here, but this is just testing that they work on bytes as well as integers. Okay. So let's have our implicit conversion test, and then we have this class that's just testing that the destructor has some side effects, basically, and a loop, while loop, and it runs some tests here. This, we evaluate this cos6 stuff, and then there's some main function that doesn't do anything. Okay, so these are the things that work. Next steps are going to be serialization functions, and this is going to create, serialization of structs or whatever, and then that's going to enable my val const expr, and then you could have, like this seems fairly straightforward, but we can serialize the object and then deserialize it as needed to reconstruct it. But this also allows us to have, my other, or like my string, right, which is like const expr, and we can just have like it be a string, right, and then this can be, I don't know, foo-func that does something, and then what we can do is we can serialize it after we evaluate this, and then deserialize it into a string as like the constructor of this like const expr object basically is just a deserialized string. So we can serialize and deserialize objects. So if I have my string class and it has the serialize and deserialize functions, then it can be used in const expr, because when it finishes evaluating the const expr thing, what it's going to save is actually just the serialized representation of the class. And so, this also means that you would be able to use objects that are complex as template parameters, because it would be able to just check if the serialized representations are equal. So you'll be able to use serialization and deserialization to create this sort of rich const expr environment where it's not just, primitive types like int and bool, and that can be used as const expr parameters, but also like if I have my own string or map type, I can create a const expr set of, foobar. I don't know, right? Like this would be a valid const expr potentially, is that I have a set, and I have a set of const expr, and then I can use this in other places, and it's able to construct this object by just deserializing it, which can potentially also be deserialized at compile time, which means that it can also be used in further const expr expressions as well. So we can evaluate it once, and then we get its serialized representation as well as we know its type, and then we create an object of this type, and then we just deserialize into the type to kind of create the const expr object, for evaluation in other contexts. So that is what this sort of const expr thing would allow us to do. So we can then sort of have this const expr thing evaluate things at runtime, or we'll create objects at runtime based on this. So we will just, take an object and then deserialize it, and then that can call, the runtime memory allocator while it's deserializing the object. So you can have this const expr. This is not implemented yet, so those don't work because this requires functioning serialize for at least, primitive types, and then a way to get it working for classes as well, which I'm going to assume we're going to, call the serialize function of the class. And, so for example, if I have my own class, I could write my own serialize function, or there will be a built-in one. If all of the members of your class have serialize functions, it can kind of have a built-in serialize and deserialize function. You can override it if you want, but there'll be a default one. For many classes, we'll just have a default one. So we've got these runtime statements. So if you want to check if you're in constant expr or not in constant expr, so you can just run this, change it. You see fails the test, right? This is not what it expected. Expect to get 10. Change it back, save, run it again, and we can see that it actually does return no errors. We can actually trace the execution. It just prints it currently. There's the state is a little messed up because I forgot to put the comma back in when I changed some code. But we can see, this it's kind of printing out every instruction that it invokes during constant expr evaluation. So we have like, load instruction, bitwise shift instruction, convert references, init int, make ref, jump. I changed some of the name, like mkr is now just make ref, and like LCI is init int. So a lot of these instruction names are now longer and a little bit easier to read. So if I go find the actual one of these functions here that got compiled to IR, you can see like these are a little easier to read than they are. So this is like make ref, init int, convert ref, load, compare equal, assert, jump. So the assembly or the IR is a little easier to read now than it was before in the previous version. Also slots, arguments are not really slots anymore. They're now in this parameters thing, which is not being printed for some reason. But we have these like, constant ref slot and so on. So we get this IR from the function, which can later be transformed into LLVM IR. It's not exactly the same, but it's close enough that there will be a simple conversion between these IRs and LLVM, which of course is what we'll be using for all of our code gen, at least initially, and then probably have a second translator also for like CLI, CLR, or whatever it's called. I forget what that IR is named, but we'll probably have a translator that converts this both to LLVM, and then also I want to support CLR and possibly Java. So those are kind of the reasons why I have this extra IR, because I don't want to be like entirely beholden to LLVM. I would like to have multiple different target outputs besides just LLVM. And then also, if I make a self-hosting compiler, I probably don't want to rely on LLVM because LLVM would be very hard to convert into a new language. So we've got this design where we have this intermediate IR, and then we'll go ahead and so like we've got bitwise norm, copy ref. So some of the functions that we test, this is probably our bitwise test here. Yeah. Now, as you can see, there aren't source code lines currently. This is kind of a to-do item. So like keeping track of where the source code is for each piece of generated code is still in this sort of to-do state. And so you can see these sort of SSA like slots. They're not quite the same as SSA, but they're similar. They're more like alokas, except when they're not. There are different kinds of slots and different ways you can allocate them, but basically most of these are going to look like an aloka, which is going to be optimized away by LLVM. Okay. And I think we covered our modules already, but just to recap, we have this sort of build file, and then that contains all the different options. The tests are running this one. So if I go open my test here, we can see that this test is pulling the example folder, and then it's setting the main module here. And then we target, so we throw the bundle at the compiler, and then we say what target we want, and then we're just asking it, if the constant expr test suite equals 1. That's kind of a workaround because there's no static tests yet, which will be added later on, but we'll have kind of a static test that's going to go in, and we're going to enumerate the tests and create separate test cases for each static test. That's the plan anyway. But for now, it just kind of checks that this equals 1. And of course, there's all sorts of other tests in here as well for various things. Like we have some const expressions that are just kind of native expressions, and then we test like some of the classes that are used for various things, like the dynamic input iterator, which is just type erased iterators, similar to standard function but for iterators, which I use in various places. And then we have like this order of operations test, and that is checking that it's equal to some specific thing. Well, that's actually not very extensive. Yep, and then there's this name mangler test, which is like just testing my sort of name mangling for actually generating code. These tests probably need to be updated. There's not enough of them, but most of the tests that I've been working on have been testing this sort of just this const expr test suite, which is all these functions in here, and then just relying on the assert statement to catch anything that's not working. So for example, if something is not working when it's executing this, it's going to fail an assert, and then that's going to cause the const expr test to fail, evaluating the result of this function here, right? If the assert fails before it returns 1. And that's how all the tests work currently, to make sure everything is working. And then we'll have to obviously duplicate all of this for the case where, if we are evaluating this inside of native code, we also want to make sure that the native code gen produces the same results. So we'll have another set of things to do there. Okay. Yeah, and those are the main things. So I guess the to-do items for the language are going to be serialization is going to be the main one. We still don't have global objects, and I also need storage. So having a type that's like storage for int or something will be useful for essentially like union types and user defined string. So if I want to have like allocations in const expr, so if I've got my place at, so like place at this kind of thing needs to be implemented. This is actually not implemented. If I like actually read this code, it just generates an unimplemented instruction. It does trigger an error if you execute it, but it does generate. There's actually an instruction called unimplemented. So I do have some of those used in some cases. I actually don't know if this will do code gen though. But yeah, like this is an unimplemented instruction, which can throw an error or terminate your program. So you can just be like, hey, this is not implemented. Here's unimplemented. That's a keyword. Then there will also be unreachable. This doesn't actually exist yet, but same idea. It should work a little bit differently with the optimizer though. Like if you declare something as unreachable, that could be an optimization hint, whereas if you declare something unimplemented, that's not necessarily an optimization hint. But yeah. Okay, so that's kind of the main progress. We have, array constructors working. I should go real quick over the way the array constructors work. Hang on. We got this. Actually, want the where's the IR for this thing? Actually, I'm somewhere in here. Yeah, it prints out a lot of spam. What does this be? Module 3. So yeah, so here's the array constructor here. So this is built in, it generates this. So we have this array init. So we have this array initializer type. And this type, what this does is we create this array init start thing. And that creates this array initializer. And so we branch on if there's more, right? And then, so is this copy constructor or new constructor? Okay, actually, I don't know why I use this. This is probably doesn't need to be generated in this case. That's not doing anything. But basically, what we do here is this is not actually the copy constructor. I copied and pasted some code so you can see like there's some leftover bits here. But what it does is it calls this array init element function, which grabs the element from the array, and then we invoke the constructor for that element on that element, which then advances the initializer. Because of the array initializing relationship between the parameter. So we could see like there's actually a tracked relationship between this 5 here, which is tracked as being part of this initializer. And then that, when we call the constructor with this, its lifetime transitions to alive, which also triggers an advancement of the initializer object by 1. And so we go jump back here. Sorry, we jump here, and then it's like, okay, is there more? And if there is, it goes here or there. And when we're finished, we call this array init finish thing, which transfers the lifetime control from this array initializer back to the array object. And this is mostly for just lifetime tracking and unwinding. This doesn't actually do anything at runtime, but it affects the way the state tracker is able to keep track of object lifetime. So this is just for keeping track of object lifetime. It doesn't do anything. But it does, like at runtime, it doesn't do anything, but it affects the way we track lifetimes. So we can get rid of this array initializer thing, and then we just transfer the lifetime control back to the object, and then we're just tracking if this, and then it also transitions this object here from being in the partial state to being in the constructed state. Again, that doesn't involve any instructions, but we need that if we want to generate unwind tables. So that is mostly for exception handling and making sure exceptions work correctly. And then we also have a similar thing. So I used to have struct delegate new. That is now struct init start. Works on similar principles, but we have. Oh, where's my red? Okay. There is an implied struct completion on the return. I'm not sure if I want to keep that or if I'm going to change that, but currently that is how it works. But you have the struct init start, and you assign this, and then it doesn't have more because like structs have a finite number of elements, and it's pretty reasonable usually. So you just specify all the struct fields up front. So let me look at one that has more. So this one has 2. You can see in this constructor, we did this struct init start. We initialized them both to 0, and then we returned x3. So this is one where we had some actual logic. What is this? This is the constructor, and the other object is a const reference to the same type of object. So this is the default copy class test, which this default copy is going to be like generated, but we can copy reference, access the field, load, jump, and then it creates the object here. So this here's part piece for partial. So you see this object is in partial state, and then we have this implied transition from partial to fully constructed on return for struct constructors. Again, not sure if I'm going to keep that or if I'm going to make this be always explicit, but there is a struct init finish instruction. Currently, it's not used anywhere because it would only be useful if the like function is inlined, and you would have to take that implied transition from the return statement and then put that as a struct init finish instead if it was inlined. But it doesn't currently, like that's not currently a thing. in the IR for the these implicit returns. Okay, and then we have yeah. So I think this is kind of a good overview of the state of the language. There's more things that need to be done. Um, you know, like I said earlier, we have uh, the need to add some additional bitwise operators here. We have we need some global variables. We're also probably want like privacy. Also, the fact that I can't compare two numeric literals to each other is probably a problem because I have to cast one of them to a like I can't do 2 equals 2 because there's no like bool operator for this. It's just I have to convert one of them to like an I32 or something. So I need to fix that. And then of course we probably want more um functions. Like these have to be fixed. This doesn't do anything. We need constigs per allocation, and then we'll just kind of go into code gen, I think. Because once serialize is working, I think, and then we need like more loop statements, but I think that would be like honestly the core of the language is pretty close to being done, where we can start kind of throwing out code gen and start doing something interesting with it besides just this constigs per. So we may have our demo pretty soon, relatively speaking. Oh yes, and we also need better bindings because there are a couple of double conversions here that exists. Um, so where is it? Yeah, so this is a problem. Currently this doesn't go in one step. This needs to go in one step. Like VII string constant needs to be treated as a binding instead of as an argument conversion. So this is like there are binding conversions currently. Like if I want to convert from one reference type to the same type of object, that's considered a binding conversion, which you can have an extra in addition to like your implicit conversion. You can also have your binding conversion that happens beforehand. So you can do a double convert if one of them is a binding conversion, but like this is not a binding conversion right now. And we also have a similar problem with like taking these numeric literals. Those converting those to like integer types is not currently considered a binding conversion, which it should be. So this currently requires like a double conversion. But it would be the same as if we take a numeric literal and converted it to a type that it expected a fixed width integer. That's a double conversion, which is not able to be done by as. So that needs to be fixed. And I think those are the main things. We're not going to have exception handling in the first like demo version. It's going to be exception free, even though there's obviously a lot of work that has gone into like the IR design to make sure that exception handling will work in the future, like this sort of like array initializer and stuff. We're not going to have exceptions right away. And the main reason for that isn't the IR generation, it's just the difficulty of creating an unwinder, and reading dwarf means I'm going to have to like re-implement the whole unwinding mechanics inside the like the runtime library, if I want the language to be like self-hosted, or at least have no external dependencies on this system C library or something like that, which is part of the goal. So we're gonna have no exceptions initially, but it will be a language with exceptions, and we're going to make them faster than C++ exceptions. So there are a number of things I could talk about with what I think GNU CLib did wrong with exception handling and how we're going to fix those things, and also some minor changes to the design on how exceptions are handled that should also make them a little bit faster. Okay, with all that in mind, I think that's everything. So that I wanted to cover in this episode. If you have any questions, let me know, and I will hopefully make another one of these videos relatively soon with some benchmarks and a code example of it doing something interesting. Oh, yes, and we also need function or procedure pointers. That's going to be a big one. That's going to influence, the usability of this language. Can't do type erasure without function pointers or procedure pointers, as there will be in this language. So we'll have that. Yeah. And then hopefully pretty soon, maybe have these array literals and stuff as well. Pretty soon we'll have some hello worlds, hopefully. Okay. And that's it for today's vlog. I hope to see you again soon. Bye-bye.